We are looking at two-factor studies and specifically focusing on interaction. We have two categorical explanatory variables and a quantitative response variable. In the previous video, we looked descriptively to see if we could detect an interaction in the data example that we're working through, and in fact, we did detect that there is an interaction. So now we want to see if we can infer an interaction outside the study. We're going to conduct an inferential analysis in an omnibus fashion, that is, looking for to see if there is any interaction going on in our study. We can do analysis of variance, but if we want to know specifically what the nature of that interaction is, then we're going to look at our tetrad mean differences and construct simultaneous tetrad confidence intervals for the population mean differences. So that's what we're going to do now in this video. Let me go ahead and call up my R notebook. Since we want to go down the path of inference, we should check our conditions for valid inference. The independence of observations in each of the conditions is a result of the design of the study. That is, we assume here that these guinea pigs, which were sampled from a population, were randomly assigned to conditions, that we did not do things like put an entire litter of guinea pigs into one condition, but rather we want the guinea pigs to be independent both within and across conditions. So that is not a statistics problem, except that it can influence your statistical outcomes. But to establish independence requires you paying attention when you actually design your study, when you obtain your participants for the study, and when you assign participants to the different conditions. The next condition that we're going to focus on is whether in fact we have homogeneity of variance among the conditions. And in this case, we have 6 conditions. So let me go ahead and show you how we can look at a residual fit plot here in this two-factor situation. I'm going to give you some commands that go beyond what I've done in previous videos. Let me go ahead and enter those in. Actually, I already had a code chunk saved, so let me go ahead and copy that code chunk. There it is. So notice that back up here, remember we talked about creating the model way back up here, and we weren't doing anything other than storing the model in an object called model. Now I'm going to actually use it for something. I'm going to apply the AOV function. AOV is short for analysis of variance. I'm going to apply the AOV function, which is an alternative to using the linear models function, but it adds some additional things to our analysis that are very beneficial when you have categorical explanatory variables. I'm going to save this in results, and then notice what I'm doing is plotting the first plot available with results. So let me go ahead and run that and see what that first plot is. It's a residual fit plot. It allows us to graphically look at the variability among groups. Now, if you count here, you have 1, 2, 3, 4, 5 groups, but we know we had 6 groups. What happened? Well, remember at that high level that the actual fitted values, that is what we predicted, that is the means at those high levels, were about the same for both orange juice and ascorbic acid. So when you look at this, you're looking actually at 2 groups in one here. Now looking at this, it doesn't look like there's too much to worry about. If you wonder what these numbers are here, these are actually the numbers in the data set of the points that R has considered to be outliers. How does it determine those? It has an algorithm that it determines whether something is a lot different from the other members of its group. You might look up here at this one and say, well, that 23 is not too different from the next one. But remember, those 2 points may come from 2 different groups because we've got 2 groups on one line here. Probably what you'll want to do to be able to better assess this is to look at the standard deviations, or perhaps even better yet, the variances for these conditions. And if you remember, we did create standard deviations back up here. Let's see if I can find it, where we created those standard deviations. Here they are. We created standard deviations up here. Let me go ahead and copy that and put it back down here underneath. So this will give me my standard deviations, and if I want variances, I can get that as well just by squaring those standard deviations. So let's try this. Oh, we need to print them out. Okay, so here are my standard deviations, and here are the squares of the standard deviations, the variances. Now, one of the things that I always tell my students is that what we're doing for these inferences is these conditions about variation, and the conditions about normality are not about the original scores, but they're about the residuals. And so I could get the residuals from the results. If I look over here in my environment, my results does provide me residuals. But I want to show you something real quick, and then I'll explain why this is the case. Let me go ahead and I'm going to copy this standard deviation here. And I'm going to change this so that I'm now getting the residuals from the results. Instead of the original scores, I'm looking at residuals. And when I get those standard deviations, you can go ahead and real quickly compare. You'll see nothing has changed. So it was okay I used original scores. Why do I make a deal that it's about residuals? Because when we get into more complex designs, or if you have unbalanced designs, then you can have a difference in your standard deviations of these residuals. This is a balanced design, meaning that we have the same number of guinea pigs in all 6 of our groups. That's what makes it a balanced design. Weighted means and unweighted means are the same thing. And so we don't have to worry about using the original scores in this case. Now, why did I print out the variances as well? Because typically when you read the research on how different do variances need to be before you're worried about it, the focus is not on standard deviations, but on variances. In our particular case, it looks to me like if I take the lowest one, 6.32, and the highest one, that one of them is about 4 times the other. Is that a reason for concern? It depends upon what article you read. Unfortunately, there's been a lot of research done on this, and there are different recommendations because of the different researchers, maybe the different ways they did their simulation, maybe the different ways they interpret concern. Perhaps inflation of a type 1 error rate of 1 or 2 percentage points is no concern to one person, but it is concern to another person. And unless I were to go collect all that research and study it myself and make my own determination for myself, I don't have a solid rule of thumb for you. I actually use other methods that are robust against the problems with having heterogeneous variances, and there are those robust methods out there. But in terms of regular old, plain old 2-factor analysis of variance, you can find anything from a recommendation of 1.5 times the variance, and then you should start being concerned all the way up to as long as you're within 4 times the variance. This one here is within 4 times the variance. So obviously, if you're going to buy into the don't ever be more than 1.5 times different, you've got a problem. But if you buy into the as long as you're within 4 times, some people say as long as you're within 3 times the variance. Well, 3 times the variance, we have a little bit of problem here too. But we're within, it looks like we're within about 4 times, real close. I mean, this is a 6.3 and this is a 23, so it's very close. So I might be a little bit concerned. What am I going to do here? I'm going to go ahead and plunge forward, and just when I do my report, I'm going to warn the reader that my probabilities that I'm presenting, my confidence intervals I'm presenting, I should not believe the exact confidence that I'm portraying. If I say I'm 95% confident, I'm not really. I'm something less than that because we've not met the conditions for valid inference here. So this plot here, these two sets of statistics, standard deviation and variation, are pictured within this particular graph here. Okay, so takeaway message here, I'm somewhat concerned. If this was real life research, I might find a method that is going to be more robust than the standard methods. But for now, we're going to plunge forward, and we're just going to caution our readers when I get to writing up my report. By the way, this is called the Behrens-Fisher problem. Let me spell that out, because Behrens, you may not spell it correctly unless I do it for you. It's like this. So Behrens-Fisher. This is the Behrens-Fisher problem when you do not have homogeneity of variance, and there's a lot of attempts to address the Behrens-Fisher's problem. There's not just one method, there's multiple methods, and I'm going to leave it to you to look those up and read about them or seek help when you go do your own research. Now, the other thing we need in order to be able to have our inference be valid here is normality of the residuals. And so what we're able to do, notice here I went plot results 1. What we're able to do is, you might have guessed it, is, did not copy the right thing. Let's try it again. What we're able to do is to change this to plot results 2. And plot results 2 will give us a QQ plot. And this doesn't look bad. We have a little bit of an issue here. A little bit of an issue here on the lower end. The standardized residuals here in this range here from between -1 and -2 are actually larger in absolute value terms than what we theoretically would predict for a normal distribution, meaning that those residuals are extending out further in the tail, making for a heavier lower tail. And that could lead to a little bit of a problem. Up on the upper end, things look really quite good. So not too bad, but a little bit of a problem. What happens when you get a heavier tail is that you in fact have a higher probability of rejecting the null hypothesis than what you think you have. So you can set an alpha of 0.05, but actually your alpha is something bigger than that because of values that are heavier in one tail or the other. In the case of the F-test, we only use the upper tail, but be warned, that's because we're folding both of the tails. It's like cutting the normal distribution, or a t-distribution more precisely. It's like making a dotted line down the middle and folding it over top, and so the two tails end up all in the upper tail. So this kind of thing, even though we're not actually using the normal distribution to get our critical value, it is underlying where we're getting our critical value, so it can lead to higher rejection rates. So I have a few cautions going on here. Heteroscedasticity, in which I have variances 4 times in one group what they are in another group, and a little bit of an issue here with the distribution in terms of the heaviness in that lower tail of the normal distribution. So all this is to say that seek help, or at least, very least, caution your reader that you're doing these rough approximations. Now, this particular problem here with the QQ is more addressable than the variance problem. Why? Because the central limit theorem tells us that as long as we're close to normal with a large enough sample size, and here we have 60 guinea pigs with a large enough sample size, that the variance of the normality in the sampling distributions of our means can be more assured. And so this is not going to be as much of a problem down here in this picture as it is up here in this picture. But I'm still going to be warning my readers. All right, so now that I've already set you up for maybe we're not really going to be able to make the inferences we want to the degree we want with the confidence we want, we're going to go plunge forward and do it. So let me go ahead and create another code chunk. And here I put in to get an ANOVA of our results, and this gives us an ANOVA table. And you notice what we have in the ANOVA table. We have an answer for supplement, we have an analysis of variance for dose, and we have an analysis of variance for the residual. These are considered 3 different families. And those first 2 families we don't want to focus on if we have interaction. So my eye is drawn immediately, first and foremost, right down here. And no surprise, because remember, we did detect descriptively an interaction. What we're saying here is that we believe we can infer an interaction to the population. The p-value is 0.02. If I use an alpha 05 for my decision rule, I am going to reject the null hypothesis. What is the null hypothesis? It's that there's no interaction. The null hypothesis is no interaction. Now, there's actually, we can be more precise than that. We can be symbolic about that. But for now, we're going to just hold it at no interaction. Another way of thinking of it is that we're saying that the entire set, the entire collection of tetrad mean differences in the population are all going to be 0. We, in fact, have an f-value of 4.1 and a p-value of less than 0.05, so we believe there is. Why is the homogeneity of variance particularly a problem? Because notice we're using 1 value for variance here, not 6 values. That value is 13.19. If we went back up here and looked at our variances, we see that they range from 6.3 to 23. And so that 13.19 is sort of an average of the variance, but we're using it as the variance for all of our conditions. So I'm going to go ahead and infer an interaction to the population with cautions that my probabilities are probably not correct. It gives me some satisfaction to see that I'm substantially under 0.05 to 0.02 there, so I could still be off quite a bit and yet still make a correct inference. Now that's an omnibus inference. What I'd really like to do is understand the specifics. I'd like to know, where does that interaction occur? We know descriptively, but can we say the same thing about the population that we can say descriptively? In order to know that, we're going to have to construct some confidence intervals. So I'll do that in the next video.